will start the last talk of the session. That will be given by Marco Romadini on the utilitarian factor for close relations with this dual.
Thank you. So, if we put the glasses of stone duality, cryptic semantics connects model logic with the vectors in the functor. So we have an endofunctor on Boolean algebras, which essentially adds free one layer of modalities, and this is dually related to the vectors in the functor. And the connection with model logic is that the algebras for K are model algebras, and so dually the coalgebras for V are the descriptive frames. And this gives the quadratic approach to model logic. Now, let's move this diagram to the next slide. And so we have this base duality between some spaces and Boolean algebras, and it has been extended to a larger category with the same object. But on the topological side, we have closed relations. And we will see why we got interested into closed relations, which will correspond to subordinations. We will recall what they are. Now, the vectors and the functor has a very natural extension to closed relations. And so it must have a dual. Okay, it must have a dual, and we provide a description of the dual, and the main idea. So the idea that my inner feeling is that okay, all these categories, stone R, EAS, are very natural. The vectors and the functor on closed relation is very natural, and also its description. And so inside me, oh, okay, this must have some applications. So that's my hope. Okay, that's my hope. And well, I look forward to see this. We have one application, which is actually the reason why we got interested into this dual description, which is related to an open problem in the duality. And I will mention this later. Okay, so let's go back to the basic stone duality. Now, this stone duality has been extended by Celani to duality between closed relations and certain relations on the Boolean algebra side, which are subordinations. Now, a closed relation is just a subset that is closed in the product topology, or equivalently, the preimage of closed sets is closed, and the forward image of closed sets is closed, or equivalently of compact set is compact. And so this generalizes what happens for continuous functions. And okay, let me explain why we got interested into closed relations. Well, we were interested in compact alpha spaces and dualities for them. And now the connection between compact alpha spaces and stone spaces, one connection is that every compact alpha space is a continuous image of a stone space. One example is Cleveland cover. And so a compact alpha space, you can present it via a stone space plus an equivalence relation, which tells you essentially it's the kernel of the projection to the space, which tells you which elements you have to collapse. And this equivalence relation is a closed relation. So that's the first source of our interest in closed relations. That's a relation on the same stone space, G of X. But also there's a second source of interest, namely to consider continuous functions between compact alpha spaces. Then how can we represent this function at the level of their covers? This is not a function, but rather a relation, and which in particular satisfies different properties. In particular, it is closed. So that's just a glimpse why we got interested in two-plus relations. Okay, now, what is the dual of a closed relation? Here we are in stone spaces. It's well, it's a binary relation, so a relation from the kilobits of y to the kilobits of x. Usually, what you do is you take the kilobit of y and you map it to the pre-image. So you take v and you map it to r minus 1 of v. But here, this might fail to be a kilobit. So it's just a closed set, and the way in which you say what the closed set is, you just say what are the kilobits that contain these closed sets. So you with this relation S dual to R, you say, okay, this you capture what kilobits contain R minus 1 of V. As an example, if you take the same space and the identity, the dual is just an inclusion. And in fact, you can think of these subordinations that I'm going to define as less or equal between different Boolean algebras, possibly different Boolean algebras. In fact, this is a definition of a subordination, which reminds the property of less or equal. So a finite join is related to a finite mean if and only if each element of the join is in relation to the elements, each element of the mean. And so the category of stone spaces with closed relations of multiple is dual to the category of Boolean algebras and subordinations between them. Okay, now comes the Vietoris part. So the Vietoris hyperspace is a construction in topology which assigns to, well, in our case, a stone space X, the stone space of its closed subsets, equipped with a topology generated by these subsets, a diamond U and box U, which will become lobes in this hyperspace. Essentially, they capture the closed sets that are containing U for box diamond, for box of U, and those that intersect U for diamond U. And this construction extends morphisms to continuous maps by taking the direct image. Okay, what happens for closed relations? Now, for closed relations, it has been extended, actually in the larger context of compact Hauge spaces, and essentially it's very similar to the definition of the Egli-Milner order, if you're familiar with that. And yeah, the idea is this. You have two stone spaces, X and Y, in a relation between them, which connects points of this. A closed subset here, so an element of the Vietoris space of X, sorry. Let's say a closed subset of Y is related to a closed subset of L if for every element of K there's an element, for every element of L there's an element of K related to it, and vice versa. For every element of K there's an element in L related to this. Now, okay, and it restricts, if you make a little computation, it restricts the usual Vietoris factor on continuous functions. Okay, and so we were interested in providing a description of the dual of this factor. And well, on some spaces, on objects, it was already given. And the same thing as for the dual of ion stone. So if you assign to a stone space in Vietoris space, dually you assign to a Boolean algebra. The Boolean algebra that you obtain just by taking these formal symbols, box A, diamond A for every element of the Boolean algebra. You take the free Boolean algebra, and then you quotient under essentially the axiom of Boolean algebra, of model algebras, which are box and the finite means. Diamond is the Morgan dual of box. And then, as a consequence, diamond is preserves finite joins. So we're adding one layer to a stone space, for a closed relation, we assign this Egli-Milner relation. Dually, we have a subordination, and we should assign to it a subordination. So, which is a relation between Ka and Kb. So, we should describe when an element of Ka is in relation with an element of Kb in terms of what happens. But now, if you remember, these subordinations are like less frequent. So when you want to describe when something is less frequent than another thing, it's useful if the first thing is a join of things, and the second thing is a meet of things. So we use conjunctive and disjunctive normal forms. If we have a Boolean algebra, then every element here in Ka, which is a Boolean combination of boxes and diamonds, can be written either in disjunctive normal form or in conjunctive normal form. What we mean? We mean we can write it as a finite join of meets, of finite meets, where in this meet we can assume that there's only one box, and moreover with this sign condition, which is helpful, that every AI is less frequent than B. And dually or dually, we can write every element as a finite meet of elements of this form. So a join of box and diamonds with exactly one diamond, and every C less frequent than DJ. Okay? Okay, so we have essentially we're left to describe when a finite meet of diamond and boxes of this shape is in relation with a finite joins. And let's take inspiration from a very special case which is the lesser equal. So maybe if you're familiar with topology, you can think of this AI and BI as an open subset of a stone space, and this inclusion as a subset inclusion. When is this meet below this join? Well, there are some easy sufficient conditions which just use order preservation of diamonds and boxes, which turns out also to be necessary. And this is that if C is above any of these AI, then you get this these are less or equal, and same thing if B is below D of J, you get this less or equal. And the interesting thing is that these are also necessary conditions. And we call this idea just as to remind us, but diamond with diamond or box with box was already present in the literature in some form, and this generalizes to subordinations. You just replace less or equal with these subordinations. Okay. So again, here the idea is that we can restrict to these forms, and then there's this simple condition that these are related if not if one of the diamond elements is in relation to the diamond on the right, or the same thing happens with the box. And essentially this is this gives a description for the dual of the guitarist and the functor on closed relations. So on objects, it maps Boolean algebra A to these free Boolean algebra modulo some relations, and on morphisms, maps the subordination X to the unique subordination that satisfies this diamond to diamond or box to box. And okay, so let's see. Well, the reason why we got interested into this is that we were interested in the means duality. And there was this open question about the usual guitarist construction on continuous functions. And let me recall that the duality is a duality for compact Carnot spaces, and to every compact Carnot space, you associate the Boolean algebra of regular opens with a binary relation that tells you when U has a closure that is contained in V. And the question that was left open was to describe the dual under the duality of the Vittori functor of compact Carnot spaces. This was formulated in the context of continuous functions, but it was, let's say, we meant progress when we say, okay, it's easier if we move to close relations also for compact Carnot spaces, and we piggyback on the previous result. And that's the main the description, the solution of the problem. To obtain the free dual of the Vittori functor on K house, or also on the category with closed relations rather than continuous functions, we apply first Ks and then a magnitude completion. Let me say what I mean. So you have a closed relation from a compact Carnot space X to Y, and this corresponds to a subordination satisfying certain properties between the free duals. And then on the space side, we apply Vittori's functor, while on the algebra side, well, we first apply this functor Ks because we can apply it to everything. Here is the Boolean algebra, a subordination, the degree of proximity is a subordination, and here's a subordination as well. We apply to everything. And then, in a certain sense, it is a solution already. But actually, it's not a Devries algebra, so we need it's not complete. These are not complete, so we need to complete them together to make a magnitude completion. And this provides the dual of the Vittori functor. And yeah, we can restrict it to functions, but it was useful to go to relations first. Okay, and so let me conclude. What are the key ideas that I want to convey? Some of these were already present in the literature, but I think they're worthwhile. So first of all, in certain contexts, we should go beyond functions. So go to closed relations or subordinations. I don't know where exactly this is useful, but I'm quite sure that it's useful in these dualities between spaces that are not necessarily three-dimensional, so compact ordered spaces, stably compact spaces, compact ordered spaces, and unitary structures, so things like lattice or Boolean algebra with electricity. I think in this case it's very useful to go to those relations. And we have this condition that describes the dual of the Vittori's functor. Some more or less was already present in the literature in various forms, for example, in the form of containment relations. But we package all these ideas to provide the stone description of the Vittori's functor of those relations and a dual description of the Vittori's functor of compact Carnot spaces and closed relations and its restriction to continuous functions. So you can view the details in this paper, which is available on arXiv. Okay, so let's go.